Hello, greetings, and welcome. In this screencast, we will set up our the solution to our first shortest route problem from Chapter 5. In this screencast, I will set up our problem as an integer programming problem, and then there will be a separate screencast in which I solve. Okay, so there's other strategies that could be used to solve our network problems in Chapter 5, and you can take a look at the textbook to review some of the concepts. But here we're going to use integer programming, which is in line with what we've done so far and what we are capable of solving in Excel. So here we go. So the network in the figure below gives the permissible routes and their lengths in miles between cities, nodes 1 to 5. In the three questions that follow, you will find the shortest route between two cities. For all cases, set up the integer programming problem and numerically solve. Okay, so we're going to be given three different situations in which we're asked to find the shortest distance between two nodes or two cities. We're going to formulate our problem as an integer programming problem. That'll be done in this screencast, and then we'll have a subsequent screencast in which we numerically solve. So again, there's other ways to solve it, but we will use integer programming, which is in line with what we've done so far and what we're capable of solving in Excel. Okay, so here we go. So problem 1. Determine the shortest route from city 1 to city 2. So that's node 1 to node 2. All right. So when we look at our diagram, okay, so we're going to start in node 1 here, and we want to find the shortest distance to node 2. Okay, and so I know that I'm going to be able to go directly from 1 to 2, or I see I could go, say, from 1 to 3, 3 to 4, 4 to 2. And that looks like it'd be all, right? Because I can't go from 1 to 3 to 4 to 5. I would end at 5. Okay, but we're not going to iterate over all possible solutions, right? So just looking at it, I would see that going from 1 to 3, 3 to 4, and then 4 to 5, that would be 55 miles. That'd be shorter than going directly from 1 to 2, right? So that would be my shortest route. Okay, we want to set it up as a linear programming or integer programming problem so we can generalize it. So no matter how difficult the problem is, the formulation will be exactly the same, and we'll solve. So how we solve these types of shortest route problems is we're going to imagine taking a car, say, or a unit through our network, right? And we're trying to find the shortest distance between nodes 1 and node 2. So what I'm going to do is I'm going to update or modify my network so that I have some single unit entering my network at node 1, my starting position, and I'm going to have a unit exiting my network at unit 2, or at node 2, at city 2. Okay, and then basically there's going to be two tasks. One is going to be formulating our constraints. Okay, so now when it comes to our parts 1, 2, and 3 are three different shortest route problems, and all three of those, essentially what we need to do each time is just update our system of constraints, right? Our balance equations, our node balance equations. Our objective function in all cases will end up remaining the same. Okay. So I'm going to start with the task of my objective function. Okay, and I'm not going to label this under part 1, 2, or 3 because it's going to remain the same in all cases. Okay. And actually, before I define my objective, let me define my variables. Okay. So I'm going to define a bunch of variables which will end up being binary. Okay, and my binary variables are going to indicate whether or not I go from route 1 to 2, 1 to 3, 2 to 3, and so on and so forth, right? So I'm going to have a variable for all possible routes. So I can possibly go from 1 to 2, okay? And so I'm going to use x, and then my subscript 1 will be my starting point, 2 will be my ending point. So I'll have a variable x12 if I go from, try to take this route from 1 to 2. I'll have x13. So if I go to node 2, I'll have, I already counted for 1 to 2, I'm going to have 2, 3. Okay, so I'm just going to go from nodes, or routes exiting a node. So I have 1, then 2 just has the 1 exiting, So if I go to 3, I'm going to have x 3, 4, x 3, 5. Okay, that's that. Now I go to 4. I have x 4, 2 and x 4, 5. Okay, go to node 5. There's nothing exiting node 5. Okay, so I'm going to have 1, 2, 3, 4, 5, 6, 7 possible routes. All right, so 1, 2, 3, 4, 5, 6, 7 possible routes. So I've got them all. Okay, and I said the variables are going to be binary. Okay, and so basically our variables are going to be 1 if our route is taken, and it's going to be 0 if our route is not taken. Okay, and so we'll always apply our non-negativity constraint. We're going to formulate this as an integer programming problem, so we'll have our integer constraint. And so basically we're going to add a constraint. We'll have a system of constraints that all of our variables are going to be less than or equal to 1 that'll force this binary nature of our variables. Okay, but we'll come back to that as we set it up. So our variables, we're going to have a variable for each possible route. It's going to be 1 if the route's taken, 0 if the route is not taken. Okay, so our objective is to find the shortest route. Okay, now what that's going to correspond to is we're going to try and minimize. Okay, we want to minimize the distance traveled, and that's going to be z is equal to. Okay, and what I'm going to do is I'm going to sum over all of my routes times the distance of each route. Okay, so I'll have x12 times 100, because I'm going to minimize z is equal to 100 x12 plus, so x13 is 30 plus 23 is 20 34 is 10 35 is 60 that's 35 okay, 42 is 15 and then 45 is 50. Okay, so when I write down my objective function like this, right, it might seem, why am I including all these possible routes? I'm just trying to go from 1 to 2, all right, and we just said the only way I can do that is going from 1 to 3, 3 to 4, 4 to 2, or 1 to 2. And again, we're just trying to generalize this. All right, so we're listing all possible routes as keeping those all as possibilities in our journey from 1 to 2. Okay, and these variables are going to be binary. They're going to be 0 if we end up taking that route in our journey, or if we don't take the route, it's going to be 0, 1 if we do. Okay, so we're just going to include all of those possible routes in our objective function. So our binary variable times the length of that route. And then what'll change in each case is going to be our constraints, which will correspond to our balances, if you will, on our nodes. Okay, so I'm going to keep my objective there. Okay, so then in terms of constraints, I'm going to write out my general constraints that won't change each case or each time. And so first I'm going to have non-negativity. So x1, so all my variables okay, are going to be greater than or equal to 0. This is our non-negativity constraint. I'm going to have my constraint that all my variables are going to be integer. Okay, and then in order to get this binary constraint, so we're already assuming our variables are non-negative, we're assuming they're integers, so we're going to add a constraint that all of our variables have to be less than or equal to 1. So if they have to be greater than or equal to 0 and less than or equal to 1, the only two possibilities then are going to be 0 or 1. Okay, so the last one I'm going to try and squeeze in here will be the x12, x13, x23, x34, x35, x42, and x45 are less than or equal to 1. Okay, so this is going to be, these will be my variables in general. That'll be my general objective function for this shortest route problem. These three constraints will apply in general. And then what we'll look at is the specific cases of problem 1 through 3 as we're listing them here. And that's where our next set of constraints will differ slightly. Okay, so I'm going to write out, let's call it part 1. Okay, so in part 1, we want to go from node 1 to node 2. Okay, so the next part in all these that happens is we need to continue on with our constraints. Okay, and our next set of constraints is essentially going to correspond to a node balance. Okay. So what that means is if I look at node 1, all right, I have this fictitious 1 unit entering node 1. Okay, so the units, all right, entering node 1 have to be equal to the number of units exiting via route 13 or route 12. Okay, and so now remember x12, x13, these are going to be binary variables. Okay, so let me label out all my nodes so I make it clear what my balance is. Okay, so node 1, okay, what's going into unit 1 or node 1 is going to be 1 unit. Okay, then unit 1 can exit via route x12 or x13. Okay, so these are going to be binary variables. Okay, so it'll be 1 if that route's taken, 0 if it's not. So I'm going to sum over all exiting routes times the number of units exiting via that route. Okay, so again, I'm not going to take routes 1 and 2 or 1, 2 and 1, 3. I can only take 1. Okay, so that 1 unit needs to exit via route 1, 2 or 1, 3. Yeah, so there's my node balance. So if I go to node 2, okay, as I go through things, okay, first I'm going to sum up my entering routes. Okay, so I'm going to have x12 coming in and x42 coming in. So I'm going to write this as, what's going in. I just said x12 plus x42. x12, x42. What's going out is going to be x23. And then also I'm going to add 1, right? Because I have that 1 unit exiting at my destination. So x12 plus x42 will be equal to x23 plus 1. Okay, there's my node balance. All right, now if I go to node 3, coming in, I can have x23 and x13. So I'll have x23 plus x13. So x23 and x13 is going to be equal to x34 and x35. So that's going to be equal to x34 plus x35. Okay. If I go to node 4, okay, coming in is x34. So it's going to be x34, okay, and that has to be equal to what's coming out is x42 plus x45. Okay, and then 5, what's coming in? That's x45 plus x35. Okay, and I've got a typo here. It looks like I'm going to have to fix in this. No, there's 42 and 45. No, I take it back. So what's coming in? x45 and x35. And then nothing's exiting. So that'll be equal to 0. All right, so it's this general form of in is equal to out. Okay, cool. Okay, so for part 1, there's our additional constraints. So we have our objective. Well, so we have our variables. We have our objective, our general constraints, which will essentially force that our variables take on values of 0 or 1. And then here's our constraint specific to part 1. Okay. So I'm not going to just list out the integer programming problem here, right? So we could summarize it, but then there'd be a lot of time of you watching me just trying to rewrite that. And instead, we're going to take a look at 2 and see how 2 would change. Okay. So now 2, we're going to try and find the shortest distance from city 1 to city 5. Okay, so what's going to change is I'm going to insert one of these fictitious units in route 1 or node 1. All right, I'm going to try and take this, say, one car, this one unit from, instead of route 1 to node 1 to node 2, I'm going to go from 1 to 5. Okay, so my fictitious unit is going to exit here at 5. And if I wanted to iterate over things, right, it looks like I could go, 1, 3, and then 3, 5. I could go 1, 2, then 2, 3, 3, 4, 4, 5, or 1, 2, 2, 3, 3, 5. And so at least here it looks like I have more choices in terms of, or options in terms of getting from 1 to 5. Again, we could just iterate over all possibilities, calculate that distance, and select the shortest route. But what we're trying to do here is generalize the problem as an integer programming problem, so that no matter how complicated the problem could become, that we could solve it just the same. So that if I had 100 cities, all right, so say this is some trucking problem. If I have 100 cities, and I have 200 possible routes, being able to generalize this and have the computer solve it for me. Okay, so part 2, we're going from 1 to 5, so now I have one unit exiting in unit 1 and one exiting from unit 5. Okay, so I'm just going to update these balance constraints. So I'm going to write out nodes 1, 2, 3, 4, and 5. Okay, and all that's going to change is 1 will be the same. 2 is no longer going to have this plus 1 since there's no longer a unit exiting at 2, but instead that one unit's going to be leaving 5. Right? So we can go through everything. Okay, but it's pretty straightforward. Okay, then I'm just going to go through and rewrite everything. So unit 2, I no longer have a unit leaving. It's no longer my destination, so I eliminated that plus 1. City 3 or node 3 is exactly the same. Okay. Node 4 or city 4 will be exactly the same. Okay. And now node 5, I'm going to have a unit exiting. All right, so put that one over on the right hand side for exiting. Okay. And that's it, right? And then I would just, update my Excel sheet and solve. Okay. Part 3. Okay, part 3, we're going from 4 to 3. Okay, so now we're going from 4 to 3. Okay, so if I were to update my constraints, okay, so pictorially now, what's going to happen is that this fictitious unit that I add comes in at node 4 and leaves at node 3. Okay. And so we could, go through and work out all of our balances. But it's easy enough just to update our constraints from parts 1 and then 2. Okay, so I no longer have a unit entering node 1, so it'll just be 0 is equal to x12 plus x13. Node 2, okay, it's the same as the last part. Node 3, okay, so now node 3 is where I'm leaving. Remember, my balance is in is equal to out. Okay, so what's coming in will be exactly the same. What's going out now, I'll need to include this exit stream. Okay, node 4, okay, in equals out. Now we need to include this unit entering node 4. So 1 plus x34 is equal to x42 plus x45. And then node 5 would be unchanged. Well, no, it's not unchanged. I no longer have a unit exiting node 5, right? So it's back to 0. Okay. And so that's all that would change from parts 1, 2, and 3 would be our constraints resulting from this node balance. Okay. So that's us formulating our shortest route problem for these 3 cases. So I'm going to stop this video. We'll jump over to LibreOffice Calc and we'll solve. Okay, hope that helps.